When going through your day, you might not realize how much mathematics surrounds you. From the intriguing patterns in nature to the wonders of music, there is more to mathematics than you think. Let us explore the beauty of mathematics in our everyday lives.
The Fibonacci numbers are a special sequence of numbers in mathematics, as each number in the sequence can be obtained by taking the previous two numbers in a sequence and adding them up together. Well, the question is, what does that have to do with the sunflowers? Well, as it turns out, the number of petals you can find on the sunflowers oftentimes follow the Fibonacci sequence. In this case in particular, you'll see that there are 34 petals on the sunflower. As it turns out, the spirals, they are not unique to the sunflowers. You can in fact find them on other areas in nature, such as by looking at the shells that you find on the beach, or by looking at other plants from above.
My name's Keith Liddett. I'm an Australian filmmaker. And I'm known here in Singapore for my Lion City series of films. I've been spending about the last 11 years revisiting the same 100 camera positions around Singapore, showing the city skyline changing over time. And one of the biggest challenges in very long-term time-lapse work that I do is that you have to find a mix between very dreamy, beautiful, slower landscape scenes and also those same scenes where you see the whole city changing and transforming over time. And so what I am looking for is basically ways in which I can sort of elegantly change the speed of scenes. So to basically start with scenes which are slow and dreamlike, move into the rapid landscape changing, and then ease the footage out in a way which looks natural and slower at the end. And that way you have a real balance in types of footage within the films. And the way I use Fibonacci numbers, that is the numbers 1, 1, 2, 3, 5, 8, and so forth, is it creates a really nice pattern which creates a smooth ramping up of speed and then a slowing down of speed at the other end. So it's quite an elegant way of basically providing speed ramps between many different sets of footage. So if you imagine that I'm filming a whole lot of little building blocks of footage, which could be, for example, a construction sequence which finishes with plants growing at the end of that sequence. I will use the Fibonacci sequence to basically ease and speed up the footage into a rapid time lapse, and then I'll use the same reverse of that Fibonacci sequence to slow the footage down at the end. And what that does is creates a really nice way of speeding up and slowing down footage which looks natural and doesn't look like it's just been basically stacked on top of each other at the same speed.
Fractals are a beautiful fragment of mathematics. They have a pattern that keeps repeating after zooming in. In other words, this pattern is never-ending. It is fascinating to see such intricacies everywhere in nature, from river deltas to lightning streaks, and to even the structure of leaves.
Mathematics has significance in sports. The path of a ball, when thrown into the air, can be represented by a parabola. This can be modeled by a quadratic equation. Depending on the person's height and the horizontal distance between the person and the rim, we can obtain unique equations representing the trajectory of the ball.
We are going to shift our focus to the architecture around us. Symmetry is exploited everywhere, especially when it comes to photography. It offers the photographer an aesthetically pleasing perspective. Symmetry can be found in places such as Zhuo Changi, Expo MRT Station, the Buddha Tooth Relic Temple, and the Victoria Theatre and Concert Hall.
Interesting curves appear everywhere. Here in the heartland Pongo, the arch of the bridge in the background appears to look like a parabola, but it is actually in the shape of an inverted catenary. The catenary can be modeled by the hyperbolic cosine function, which plays a pivotal role in hyperbolic geometry.
We are now here at the National Stadium, which is immediately recognizable as its top is dome-shaped, or rather spherical. A spheroid is an example of a quadratic surface, which is a generalization of the four conic sections, namely the circle, ellipse, parabola, and hyperbola. At the Fountain of Wealth, one of the tallest fountains in the world, notice the top of the structure is shaped like a donut. Mathematically, we call this a torus. The jets of water cascading down the ring resemble another quadratic surface, which is known as a hyperboloid of one sheet. Sounds complicated.
Calculus has many applications around us, most prominently where we wish to find the maximum or minimum of a function given a constraint. Differential equations play an important role in our everyday lives too. In particular, when studying biological systems to interpret the interaction between two species, the Lotka-Volterra equations come into play. This is what the pair of equations look like, where x and y denote the number of prey and predators respectively. dx over dt and dy over dt are the instantaneous growth rates of the two populations. The prey population is dependent on the predator and vice versa. The Lotka-Volterra equations are an example of a population growth model, and it is used in mathematical modeling scenarios. Time to head off to the next destination.
In Singapore, public transport has high ridership. When taking the MRT, we are interested in travelling to our destination using the shortest path possible. This brings us to another branch of mathematics called graph theory. And no, it is not the study of graphs, but rather the network of points connected by lines. More formally, the points are known as vertices and the lines as edges. The shortest path problem is a problem that involves travelling between points. The distance between two stations can be regarded as a weight. So the problem translates to finding a journey with the smallest sum of weights. For example, when going from Bishan to Bugis, it will be better to travel to Newton first, before changing to the downtown line, rather than going to Paya Lebar before transiting to the east-west line. We can extend this result to travelling on roads. In graph theory terminologies, cities are coined as big graphs. Applications such as Google Maps can help identify the shortest or fastest paths to our destination using an algorithmic approach.
An ellipse is in the shape of an oval. It contains two foci, which are equidistant from its center, and it lies along a straight line called the major axis. One nice geometrical feature of the ellipse is that any ray that emanates from one focus of the ellipse will be reflected in such a way that the reflected ray will pass through the other focus of the ellipse.
Here the rain oculus has the Marina Bay Sands. The top here is in the shape of an ellipse. Now if I were to stand close to the edge of the oculus, I will be able to hear what the person at the other side will say due to the reflective property of the ellipse. Let's try it. This is to test if the reflective property of the ellipse works.
Who would have thought that mathematics is infused into games? The mathematics behind the game Monopoly is that it hinges on something called Markov chains. In the field of probability, Markov chains allow one to determine the probability distribution of pieces on the board after sufficiently long play.
There are 43 quintillion ways to scramble a Rubik's Cube. There is some complicated mathematics behind solving a Rubik's Cube, and this belongs to the realm of group theory. The Rubik's Cube has been used as an illustration of permutation sets, where each rotation of a layer of the cube represents an arrangement of the surface colors.
Other than the Rubik's Cube, piano chords also have strong ties with group theory. Constructing a 12-sided polygon with the 12 notes bounded within the chromatic scale, we can form a square comprising 4 notes. When played, the resulting chord is an example of a diminished seventh. No matter how we rotate the square, we always obtain a diminished seventh chord. This process is known as inversion, and composers use this technique to control the sequence of chords and produce great pieces.